question is, if we have a reaction in which we're essentially burning ethene, right? Okay, we're burning ethene. Is it spontaneous? All right, so ethene, what does the prefix F mean? 2. Meth is 1, eth is 2, so that's 2 carbons. And what does the ene tell us? Double bond. And since each carbon has to have 4 bonds, they already have 2. We only need 2 hydrogens on each carbon. Interesting. I've been watching this series Cosmos. Have anybody watched? Any of you watched that? Huh? A bad show? Oh, it's a fantastic show. And they actually cover the fact that carbon needs 4 bonds. Okay. So if you're watching it, you get some test review, even though you aren't, doing anything in class or any homework. C2H4, that's ethane, okay? Or we could write it, ethene. We could write it CH2CH2 if we're writing a condensed structural formula 2, okay? All right, so we're burning ethane. Anytime you're burning something, you're reacting with oxygen. Anytime we're reacting a hydrocarbon fuel with oxygen, we always get the same products, CO2 and water will be in the form of steam. Anytime the carbon chain is 5 or less, we said in this class we'll sort of generalize that to mean that we're going to have a physical state of a gas. We want to know whether it's spontaneous or not. We need to balance the equation to help us figure that out. So let's see, we got carbons and hydrogens and oxygens. We're going to perform an atom inventory. That's what we always do in this class. So 2 carbons, 4 hydrogens, 2 oxygens, 1 carbon over on this side, 2 hydrogens and 3 oxygens. In order to balance an equation, you have to leave the formulas alone. Once the formulas are set, you don't put any numbers or change any numbers in the formula. You only change the numbers in front of the formula. So you put coefficients here to balance it. I have 2 carbons on the left and 1 carbon on the right. We have to balance it because we want to make sure we're following the law of conservation of mass here, because we have to have the same number of atoms on both sides. So I need 2 carbons here. That's the coefficient that I can put there. That's going to change the number of carbons and oxygens. I now have 2 carbons, and I've got 2 times 2 or 4 oxygens here, plus the 1 oxygen here, so I've got 5 oxygens on the right-hand side. I want to save oxygen for last. I'm going to balance it last, so I want to go to hydrogen next. I have 4 hydrogens on the left, 2 on the right. To get 4 on the right, I put a coefficient 2 here. That's 2 times 2 or 4 hydrogens, but it changes the number of oxygens now. I've got 2 times 2 or 4, plus 2 times 1, that's 2. 4 plus 2 is 6 oxygens on the right. And to get 6 oxygen on the left, I'll put a 3 coefficient in front of the oxygen, and that is going to be now 6 oxygens. Okay. In terms of delta H, if we want to find out if the equation or this process is spontaneous or not, we're going to use the Gibbs free energy equation. And so we got these terms here like this. Delta G is the Gibbs free energy. It means the change in Gibbs free energy. If this term is negative, then this is a spontaneous reaction. And that's equal to delta H minus absolute temperature times delta S. Okay, now delta H we think of in this class, to simplify things, we think of delta H as being the change in heat energy or energy in the system. Now remember that you've got the system. That's where the chemicals that are physically or chemically changing are. And it's only those chemicals, okay? Anything around that, other than those chemicals, is a surrounding. If I were running a chemical reaction in a beaker of water, so I take one chemical, dissolve it, another chemical, dissolve it, and put those 2 chemicals together, pour those 2 liquids together, I get a reaction. The water is not part of the system. The water is part of the surroundings. The only system is the chemicals themselves and how they change. Okay? So the system here is just these chemicals, all right? So the system is what we're talking about here with delta H. And in the system cannot gain energy. The universe can't gain or lose energy. Okay, we cannot create or destroy energy. We can only move it around somehow. So the system, we can move energy out of the system to the surroundings. Oh, UNDS. Still can't spell. Surroundings. I know that looks sloppy, but anyway, we can only move energy from the system to the surroundings or from the surroundings to the system. And that energy we're talking about here, we're simplifying it to say that's the delta H. So if I'm moving energy from the system to the surroundings, that means the delta H must be negative because the system is losing energy. The change in energy, delta is change, H is enthalpy. We're changing the amount of energy and we're losing energy in the system, so that's delta H. If I'm moving energy from the surroundings into the system, then the delta H must be positive. Does that make sense? So exothermic reactions, those that give away energy from the system to the surroundings, that's always a negative delta H. Endothermic reactions always are a positive delta H, okay? So our delta H term is going to be positive. Temperature is the absolute temperature scale, JJ. It's always positive. You can't go below 0 Kelvin, all right? So this is going to be positive. Delta S, we need to figure out what's going on with that. Well, the simple way of figuring out delta S is what's happening with the particles. Get a question?
How do you know that delta H is negative or positive in this?
I'm sorry, I said positive is negative, isn't it? No. I just said it down here and I went and marked it positive. Okay. So delta H is negative. Yeah. Delta H is going to be negative because the energy is going from the system to the surroundings. All right, because this is an exothermic reaction. How do we know? Well, all combustion reactions are exothermic. They're giving away heat. Okay, it wouldn't be combustion if it didn't give away heat. Combustion is the reaction of some substance to oxygen that produces, well, for us, we're always using these hydrocarbon fuels. So with a hydrocarbon fuel, our combustion then always produces carbon dioxide and water, light, and heat. And since we're producing light and heat as a product, then this is an exothermic reaction. Okay? And so if we're giving away energy, delta H is going to be negative. All right? T is going to be positive because we're using the absolute temperature scale. Now, there's a lot to delta S. Delta S is the change in entropy. It's the amount of disorder. S is a measure of disorder in the system. Solids have, comparatively speaking, low disorder. They're pretty ordered. Solids, the particles, at the tip of my fingers over these particles, they're stuck together. Both they're touching and they're not moving around each other. They're stuck in place. They can twist and wiggle, but they don't move around each other, okay? Liquids move around each other. So solids are more ordered than liquids. Liquids are moving around each other and touching. Solids are stuck in place next to each other. Okay, that makes sense? Okay? Now gases are completely apart. They're flying apart. They're even more disordered, less ordered than solids and liquids. Okay? But in this case, we're not talking about changing any physical states. Everything's a gas. So the other thing to know is that if I have more particles, if 5 gaseous particles have a certain amount of disorder, 10 gaseous particles will have even more disordered, or more disorder, so long as the pressure doesn't change. Pressure affects everything. We're not going to worry about it. We're assuming we're at atmospheric pressure, so the atmospheric pressure doesn't change, okay? Does that make sense? Now, we didn't get into that in this class, but just kind of giving you a heads up. Pressure affects this amount of disorder. So if we increase the number of particles, gaseous particles, there's more of these particles moving around, there's no change in pressure, and so we would increase the disorder by increasing the number of particles. But we didn't do that. We have 4 particles on the left and 4 particles on the right. Now there's 2 ways to approach the problem here. Both are going to give you the same answer. Let's start with the argument that disorder didn't change. We're going to say that's 0. There's no positive or negative change. That makes sense? You with me on that? If we didn't change the number of particles, the change in disorder is nil. Yes? All right. So this, huh? Yeah. I'm saying there's no net change in this order. Okay. So what is delta H going to be? I mean delta G. What's delta G going to be? Negative. So is the reaction spontaneous? Huh? Yes. If delta G is negative, reaction spontaneous. That's one argument you can make. There's another argument, and in fact, I suppose the third argument would be both of these together. The third argument, next argument would be this. Since when I react these two together, I'm creating heat, and so these products are going to be at a higher temperature as a result. They're moving faster than these would be. Does that make sense? Is that more disorder or less disorder? More disorder. So you could argue then, in our second argument, this is our first argument here. Our second argument here is that delta H remains negative. Our temperature term is positive because it always has to be. And we're saying that we're going to be more disordered. That's a positive delta S. All right, you with me on that? Because these are going to be existing at a higher temperature because of what we did to them. Okay? What is delta G going to be? Still negative. This time this is positive, times that negative still makes this negative. So it's a negative plus a negative, delta G is going to be negative. Does that make sense to everybody? See what's going on? If you aren't, let me know now so I can help you with it. Yeah?
There's going to be an endothermic thing?
Yeah, it could be. Sure. Okay. I'll do it after this. Okay, let me finish this. Okay, so our second argument is it's still going to be spontaneous because delta G is negative in this case too. Okay, a third argument we combine both of these. Okay, we have no net change in the number of particles. We are increasing disorder though because we're increasing the temperature here on this side. This is going to exist at a higher temperature than this does, and so this is more disorder than the original was. We're increasing disorder. It's going to be positive. Overall, then, you've got a positive entropy change, a negative enthalpy change, and that gives us this delta G that's negative. The reaction is spontaneous. Does that make sense? All right. So then I was asked to do something that's endothermic. A real simple endothermic reaction is the hydrolysis of water or splitting of water. So here's our water molecule. We're going to split it into H2 and O2. Okay? So we're going to balance this, and you should be using an atom inventory. For this process, I'm going to skip the atom inventory, okay? You with me? You're required to do an atom inventory, but I'm going to skip it today just for speed. Okay, just to speed it up. So I need two of these, right? And then I need two of these to balance it out. Yes? So this is a liquid. This is a gas, and this is a gas, okay? It's endothermic because I've got to put energy into this system. All right, if I were doing a reaction energy diagram here for this, we're starting out with two water molecules, and we're ending up with two hydrogen molecules and one oxygen molecule, okay? So this is the reaction progress to the right. Okay? We're proceeding to the right with the reaction. We're looking at the amount of energy in the system, and this particular energy is the enthalpy energy is what we're talking about here, okay, for the most part. Okay? Energy in the system. So since what I have to do to make water doesn't just naturally split into hydrogen and oxygen. Would you agree with that? It naturally splits a very small number into hydrogen ions and hydroxide ions. That's our acid-base stuff we talked about. But it doesn't just naturally split into hydrogen molecules and oxygen molecules. To do that, you've got to add electricity. You've got to put some salt or acid in the water and run electricity through it, and you'll get hydrogen gas and oxygen gas. And so since we have to put energy into this system to make it happen, these products over here are going to have a higher amount of stored energy than the reactants did. Okay? But the energy we put into it from running electricity through it, that gives us that activation energy. We got to bang those, well, let's see. We're actually, it's not really banging the molecules together. It is, but we got to move electrons around. Don't worry about how that happens too much right now. We're making those molecules bang into each other, and we're moving electrons around in the process. And so we've got this activation energy hill where the molecules are hitting each other, and we're putting these electrons in there from the electricity, making this happen. So there's the activation energy hill from adding the energy, the electrical energy. And so here's our activation energy here. The change in enthalpy overall is this. We're increasing enthalpy. Delta H is going up, and therefore delta H is a positive term. Okay? So that's a reaction energy diagram for this endothermic process. Okay? Now let's put it to the test with Gibbs free energy. Okay? With Gibbs free energy, delta G equals delta H minus T delta S. Okay? Looking at the number of particles and physical states, would you say delta S is going up or down? Are you becoming more ordered or less ordered? Less ordered for two reasons. Liquids are more ordered than gases, and we have 2 particles versus 3. So for 2 different reasons, we've got a positive delta S, more disorder. Okay? How about the change in enthalpy? Positive or negative? Yeah, we said it's positive, didn't we? Because we had to put energy into it. All right. So we've got a positive minus, and temperature has to be positive. Now remember, delta S is almost always smaller than delta H. Okay? Delta S is almost always smaller than delta H. Sometimes. Under what conditions then would delta G be negative? If delta T is large enough to make this whole term altogether larger than delta H. Okay? So, delta G will be negative if T is large enough. Does that make sense? Alright? So then, we run this reaction at normal atmospheric temperatures. Is it going to be positive or negative? We don't have a large temperature, because that would mean larger than normal atmospheric temperatures. Huh? Delta G is positive. This is not spontaneous. And we know that's the case because we had to have energy, add energy to it to make it happen. All right, so let's look at this reaction and this Gibbs energy idea, this concept behind Gibbs energy and spontaneity, to write a claim and justification. Okay? So what is our claim? That this reaction is will occur on its own, or it won't. Is it spontaneous or not? It's not spontaneous under normal atmospheric conditions, where temperatures are, 0 to 100 degrees or something. Let's just say that, all right? So our claim is that this reaction is not spontaneous without very high temperatures. Okay, so now we got to support that. We got to have a justification. All right, we got to nail it down. All right, we got to go into court and convict somebody. Okay, without a shadow of a doubt. All right, make sense? All right. So first thing we can say is we know that this reaction has a positive delta H because it doesn't happen without adding electricity to it. Does that make sense? We're adding energy to it. So therefore the system is gaining energy and delta H is positive. So Alright? Temperature is always positive. Gibbs equation uses absolute temperature. Alright? The entropy is increasing because gases are more disordered than liquids, and because are more product particles produced. All right? Under these conditions, delta G will only be negative if the temperature is high enough. So, this reaction will only be spontaneous under very high temperature. All right?